Good morning. We are ready now to move into Chapter 5. We finished up Chapter 4. I hope Chapter 4 was actually a lot of fun, that you're able now to take objects and analyze the forces that are acting on them, and then from that determine what their accelerations will be. Once we know the accelerations, then we can answer questions about how far is this going to travel, how fast will it be going, what's it going to look like as a function of time. Chapter 5 is more of the same. And so Chapter 5 we're going to be introducing frictional forces, which is going to make everything much more realistic. And then we're going to be looking at circular motion, and we'll be looking at resistive forces. We'll be looking at air and fluid resistance. So all of these are going to broaden the range of problems that we can look at. So let's do this. Here's a list of topics that we're going to be looking at in Chapter 5. You're welcome to take a look at those. Friction. So friction's always present. Here's a block. We're going to be pulling this off to the right. Now I feel like that shouldn't be a velocity. It should be the velocity vectors. I'm going to say need to be off to the side, because vectors right on the objects now are going to be the forces. We've practiced so much in Chapter 4 setting up force diagrams, otherwise known as free body diagrams. Now what they're showing here though is that there's always friction going on between surfaces. So there are, sometimes the surface is just rough. Even smooth surfaces, if we look close enough, there's going to be some variation in the surface. And then what also happens is materials attract each other. You can have these tiny molecular forces, you know, the molecules on one side of the surface and the molecules on the other side. There's leftover electric forces acting between those two sides. And so you can have adhesive forces acting between surfaces. So in the last chapter, we had friction in some problems, but for the most part, the examples that we looked at in detail did not include friction, but now we're going to include friction. So, and what this is saying is, friction's complicated. You know, there are still people and, you know, scientists and engineers out there that are, you know, their career, they're spending their careers looking at friction and how to best understand it, and in many situations trying to minimize the amount of friction in a particular situation. And maybe another example is trying to maximize friction, like if you're designing tires for a car. So we're going to use actually a pretty simple model. The formulas that we come up with here for friction, they work okay. They work pretty well. And so what we want is just some kind of formulas that will provide us with kind of a reasonable description. But remember, there are going to be limitations to the frictional force formulas that we come up with. So it's fine to try and understand friction in terms of these formulas, but remember, friction can be more complicated than what we're writing down. Now, we're going to talk about two different types of friction. One of those is called sliding friction or kinetic friction. So kinetic friction is when an object is actually, you know, the surface where the two objects come into contact, you know, the book, for example, is sliding along the tabletop. So I got the tabletop surface, I got the book surface, and they're sliding past each other. What we find, this is our simple model, is that the frictional forces that we find are given by a coefficient. Now this is referred to as the coefficient of kinetic friction that tells us something about the surfaces. So if the surfaces tend to be more rough, if they tend to be more kind of sticky, more adhesive to each other, then the mu values are larger, and if the surface is really, really smooth, then the mu values are small. And so what this formula is telling us is that the sliding frictional forces are proportional to the normal force. And you go, well, that's kind of interesting. What does that even mean? If I slide this book back and forth, it says that the frictional force is proportional to how forcefully the two surfaces are pushed together. With how much force is the book being, pushing, how much force is the book pushing against the table, and how much is the table pushing on the book, and those are going to be the same magnitude. It depends on how much force there is acting between the surface. So there's a certain amount of friction right now, and that's based on the normal force. And if we do a diagram, we would say, well, the normal force right now is being determined by a gravitational force. If we take an object, set it on a surface, there's a gravitational force downwards, so the normal force along the surface will match whatever the gravitational force is under those circumstances. Now, if I push down on the book and then try and slide it back and forth, what I find is the frictional forces are bigger. If I take the surface between the table and the book and I push so that the normal force between them is even larger, then the frictional force goes up. Now what this is stating is that the frictional force goes up proportionally. So if I take two books and stack them together, then the frictional force between the table and the lower book is going to be twice as large. If I take 3 books or 10 books, the frictional force will go up proportionally. Now, there's a lab that we will do. One of our labs will be looking at this and seeing if the proportionality constant approach works, and it works pretty well. So we do find that this gives us a pretty good model. It's a pretty good representation of how the frictional forces work, and it's easy. It's a pretty easy model to work from. So we're going to be saying that the frictional forces, when objects are sliding, the frictional forces are proportional to the normal force. Now, okay, what we're going to have to do then is look up these coefficients of kinetic friction and ask ourselves how large are those values, and we're going to get to that. So there's a table here, coefficients of kinetic friction, and that is a Greek letter mu, and then it's a little k for kinetic. So we'll get to this table and look at it in just a minute, but we want to talk about a different sort of friction. So we said there's sliding friction, but there's also static friction, and static friction is a little trickier. Let me point out one more thing before I move on that I failed to include, and that is, notice that the sliding friction, our simple model says that it does not matter what speed the object is sliding at. It's independent of speed. So it could be sliding very slowly, or it could be sliding at a much higher speed, and what this formula is claiming, and which may not be entirely accurate, is that going fast or slow, the sliding friction is going to have the same value. And that's kind of an interesting feature of our model. Again, it's not a bad estimate as to what the frictional forces will be like. Now, the other type of friction, static friction. So that first one we introduced was called kinetic, and that meant the surfaces were sliding past each other. This one is called static, and that means that the surfaces are not sliding past each other. So again, if we take the textbook as an example here, if I push on the textbook and it doesn't move, that's not because the textbook has a lot of mass. It's because there's a frictional force opposing the force I'm pushing with. So I can find out just how large that static friction can become. If I don't push at all, the static friction doesn't push back at all. If I push with a little bit, maybe a Newton, static friction's pushing back with a Newton, I push with 2 newtons, 3 newtons, 4. What we find is, at some point, we are able to overcome the static frictional force. So, again, static friction is going to be a little complicated because the static frictional force that we end up with could be any value between 0 and what we consider to be the maximum value. Now, the formula they have here says that the static frictional force is less than or equal to some maximum value, and for this they're using, again, it's a coefficient of friction, but this time it's the coefficient of static friction. And the largest frictional force we can obtain is going to depend on the materials so that we're working with, and that's what will determine the coefficient of static friction and the normal force. So we're going to bring the normal force in here again and say that the static frictional forces, the maximum values, are dependent on what the normal force is. So this book by itself, it doesn't take too much of a force to have it begin to slide. But if I push down on this, and then I try and push it, I find that there's more static frictional force than there was when the normal force was not so large. So increasing the normal force can provide us with more static friction. Now, typically, what this is saying here too is that usually it's easier to keep an object sliding than to get it to begin to slide. Static frictional forces, the maximum static frictional force, tends to be larger. And so that says that when we look at this table of coefficients of static friction and coefficients of kinetic friction, what we find is that, here's a couple of wood surfaces. Now, how many different types of wood surfaces are there? And there's like, a million different variations on this. They're claiming that the static frictional coefficients are maybe somewhere around 0.4, and the kinetics are somewhere around 0.2. Notice they're only using one significant figure here, and that's because friction can be so dependent on the details of the materials. They're saying that ice, sliding on ice, has a static friction of about 0.1. Now you'd think that would be really, the ice is going to freeze against other ice. That complicates it too. For kinetic friction, ice on ice goes down to 0.3. So ice apparently slides pretty well on, so as these go lower, things are more slippery. Lubricated metal, static friction 0.15. Once it gets moving, it drops to 0.07. Rubber on concrete. Is there rubber on asphalt? I guess I was wondering about, tires driving around. So rubber on dry, concrete, maybe it's a surface. The coefficients go as large as 1, okay? What is that, 1 to 4? Rubber on other solid surfaces. Oh, I see. So tires have really large coefficients of friction. Tires are designed to have really large coefficients of friction. Now, when you're driving, are you using kinetic friction or are you using static friction to drive? And think about that. Now, the wheels are going around. It seems like something's moving, except when the tire comes around and hits the pavement, there's no sliding that takes place, right? Tires are designed and people are told to drive in a manner where no sliding takes place. So we actually use static friction. The frictional forces that allow us to speed the car up and slow the car down are designed so that we're using static friction. If we're spinning our tires on the pavement, that would be kinetic friction, and that's frowned upon. If you go to the DMV and take a driving exam, definitely circle the letter that says, I promise to drive using only static friction at all times. I will never resort to kinetic frictional forces in driving. Of course, I guess you have to. If you hit a patch of ice, then it goes kinetic. You begin sliding over the ice. So at all times possible, I promise to use static frictional forces and avoid using kinetic frictional forces in order to better control my vehicle. So you can see some of these synovial joints in your limbs. So there's my elbow, there's my shoulder. Coefficients of kinetic friction, 0.01. Feels pretty good with those low frictional coefficients. All right, so here is that same box from chapter 4. It's still 10 kilograms. It's still a mystery box. Apparently no one has opened it yet. We're saying that the coefficient of static friction for the box on this tabletop. Now notice the coefficients of friction depend on both surfaces. It's not just this object has a certain coefficient. You have to know what the other surface is. So this is the box resting on the floor, or I'm going to say tabletop because I don't want to have to lean over and pick it off the floor. It says that the static coefficient is 0.4, the kinetic coefficient is 0.3. Now, let's see if we can, A, B, C, D, E, what force would be needed? Oh, I see. So at different amounts of force, what's going to happen here? So what we need to do first, I think, is we need to do some calculations here. Okay, so I'm going to jump ahead to this picture. So here is a force that I'm pushing with. Here is my normal force coming from this surface. Here is mg. Oh, there it is, friction. Yes. So we're going to finally get to be a little more realistic here with some frictional forces. M is 10 kilograms. Mg is 98. That's my gravitational force. The object is not accelerating vertically. So it's not accelerating upwards. It's not accelerating downwards. And that tells us that the normal force is going to be equal to mg. So that's what's going on in the vertical direction. Now that's going to give us 98 newtons of normal force, and the normal force is important because that's what we're saying will help determine what the frictional forces will be. So if there's 98 newtons of force of the table pushing on the box and the box pushing on the table, if that surface right there has a normal force of 98 newtons, the maximum static frictional force we would get is mu sub s times n, where mu sub s is 0.4. That gets multiplied by n, and that says the largest static frictional force possible with these surfaces, and for this object, not just the surfaces, but the normal force is helping to set this, is going to be 39.2. So once I push, let's see, or pull, I guess. So I'm pulling this object, or pushing it from this side. So I'm exerting a force on this object in the forward direction, and I push with 0 newtons, nothing happens. 10, 20, 30 newtons, nothing happens. 35 newtons, nothing happens. 39 newtons. But when I get to 39.2 and above, then this breaks free. Now, friction, again, friction's complicated. It's not that easily reproducible each time. Notice they only used one significant figure on many of the coefficients in that table. But we're going to say that this is reliably 0.40, so reliably at 39.2 newtons. We no longer have enough static friction force. So let's answer that question A, B, C, D. What happens at 0 newtons? What happens at 10 newtons? What happens at 38? What happens at 40? So at 0 newtons, the static friction force is 0. At 10, the static friction force will be 10. At 38, we have not yet exceeded 39.2, so that's going to be 38. But look what happens at 40 newtons. When I push with 40 newtons, the object begins moving. And so now, we are no longer, and this says at rest. More generally, what it should say is no sliding. No sliding has occurred yet. No sliding, no sliding, no sliding. Because we could have an example like this. We could have a book, and then we could have something sitting on top of the book, and if I move the book back and forth, and the object on top is not sliding, that's static friction. Even though the objects are moving, you could have static friction on a moving object. I mean, I'm standing on the surface of the planet is moving, but it's, there's, anyway, I'm writing this as at rest, but more generally, it's saying there's no sliding taking place. But at 40 newtons, sliding begins. So, or at 39.2 newtons, sliding begins. Now, what we have to do now, though, is, since it's now kinetic friction, it's no longer 39.2 newtons, that's going to drop down. And the coefficient they gave us for once it's sliding, the coefficient is going to drop to 0.30. That leaves us with 29.4 newtons. So what happens then is this. This was not enough to break the static friction. This was not enough, not enough. This is enough, which means in place of the static number, we now replace it with the kinetic number. And to find out what its acceleration will be, we can take the, how much were we pushing with? 40 newtons. So it's right here. 40 newtons minus 29.4 gives us 10.6 divided by 10 kilograms of inertia. That's 1.06 meters per second squared. So that's what we're going to have for the acceleration of this object once it breaks free. So going back to that slide we had before, the way we would graph this, okay, here is the applied force. I keep pulling with a larger and larger force, 10, 20, 30, and then when I get to 39.2, right up to 39.2, the friction force is static and it keeps pace. It keeps right up with me. I'm pushing, I'm pushing, I'm pushing. There's an opposing frictional force that is preventing anything from happening. Once I exceed the limit of the static frictional force, the object begins to move. Now when the object begins to move, we are no longer in the static realm. We are over in the realm of kinetic friction. So now it's kinetic friction that I'm dealing with, and that has a lower, typically, coefficient of friction. So now it broke free at 39.2 newtons, but the frictional force opposing the motion now is, what was the number? 29.4. If we've got that yeah, seems reasonable. Okay, so that's what that graph is doing. And then if we continue pushing with a larger and larger force, the idea is that we'll get a larger and larger acceleration. And remember, our model suggests that no matter how fast the object travels, as it slides, the friction's the same. So the kinetic friction, we're imagining, just has this fixed value as long as sliding is taking place, which is in that realm over there. There's just going to be a steady frictional force, and that's what they've shown in the graph. That's the model that we're going to be using. So let's try this. This is a good example too, I think, to think about. Let's say we have a box, and I'm pushing it up against the wall. So it's not the mystery box, it's just it's a different box. So I'm pushing this against the wall. What does the force diagram look like? Because I know I can do this. I know I can take an object and I can hold it up. In fact, I can probably do it with our textbook, right? Textbook's pretty heavy, but if I put the textbook there, I can easily hold it against the wall. Now I'm not lifting, up there it goes. I'm not lifting on the textbook upwards, I'm just pushing inwards. What is holding that textbook up? And there are frictional forces. So there's going to be a frictional force along the wall. Now there's also going to be a frictional force along my hand. And so probably on this side too, there's going to be some sort of frictional force acting on that side. But they're assuming that there's no friction on that side, I think. So I think what we have to do is assume that we've got a frictional force against the wall, but that the hand against the box is purely normal force. There's nothing along the surface, there's no friction along the surface on that side. So let's try this, setting up this diagram. So here's the wall, and it's static friction that we have, mu sub s, and so there's a force of static friction holding, apparently lifting the object up because I've got a gravitational force in the downwards direction. So how do we determine the direction of static friction when something is just sitting there? I have to reason my way through that. So static friction could be in any direction as long as it's parallel to the surface. And since there's a gravitational force downwards and the normal force here and the normal force here can't accommodate that, it means that the frictional force, the static frictional force, would be in the direction opposite gravity. So the static frictional force, we have to kind of reason our way through the diagram and decide what direction we need the static frictional force to be in for a particular problem. Now, there's no slipping taking place. What they're saying is find the minimum value of F. How much force do I have to push with in this direction to make sure that it stays on the wall with no slipping taking place? And so what we have here is, well, let's look in the vertical direction. It looks like, yeah, this is my acceleration in the y is 0. So the acceleration in the y is 0, and that says that the static frictional force would need to be as large as the gravitational force. It's got to be equal to, not bigger, not less, but equal to the gravitational force. That's what's going to maintain its position. And so that's what's going on in the y direction. In the x direction, it says that there is no acceleration of this block in the x. It's not going into the board, it's not accelerating away from the board. That says that the force I'm pushing with will set up a normal force between the wall and the book. So, you know, if I'm pushing with some number of newtons here, that creates a normal force along that surface. So there's going to be a normal force between the wall and the book in this example. And so N is going to equal F. Again, that comes from saying, hey, the book is not accelerating. So N is equal to F, F is equal to N. Now, what's the largest static frictional force we could hope for? And so the idea is this. If I push really, really hard, then the normal force will be really, really big, and the static frictional force will have no problem, because the static frictional force could be really large if the normal force is large. But what happens if I begin to let go? What if I release the force, not all of it, but slowly decrease the force? Well, at some point, that normal force, when I push on the book less forcefully, the normal force is going to decrease. And when the normal force decreases, that means that we're not going to have as much friction. So what we want to do is solve for the situation where the book is just about ready to slip. So that would be the situation where the frictional force is equal to mu sub s times n. So we're using the frictional force, every bit of it that's available to us, and that is going to be equal to mu sub s times n. If we go, if the static frictional force, I guess this is it here, the static frictional force is here. In order for that diagram to work, the maximum static frictional force, this is the maximum value, needs to be at least as large as mg. So that is saying that mu sub s times n needs to be as large as mg. Well, the force I'm pushing with is equal to n. So the force I'm pushing with times the coefficient of static friction for the object needs to be at least as large as mg. So this is the necessary condition such that the book does not slide. The force I'm pushing with needs to be at least as large as mg divided by mu sub s. Now I put some number, did they put numbers in this? I may have just, I think I just added these in. So let's say that we have an object, or we just said mg. So that would be a mass somewhere around 2 kilograms. I think our book is more than that, but let's say that the textbook's around 2 kilograms and that mg is 20 newtons. If the mu sub s between the wall and the book is 0.4, then I would have to push with at least 50 newtons. Okay, so about 10 pounds of force, not a big deal. I probably was pushing with 10 pounds of force. So, and that will generate a large enough normal force, and there will be a large enough frictional force that it can offset gravitation. So it's nice to see a couple things I want to point out here too. It's nice to see normal forces in different directions. We get so used to normal forces being vertical, we forget that there can be inclines, or in this case, the normal force could be horizontal. And then it's nice to see frictional forces too in a vertical direction. So it's a good example for seeing some of these forces in directions that don't appear quite as often. All right, I don't know if this looks familiar. I'm afraid it does. The mystery box is back. And the mystery box, it's the very same diagram we had back in chapter 4, except one thing has changed. And the thing that has changed is there is now a frictional force. Okay? I mean, that was the idea, right? Is now we are going to have a frictional force acting on the box, and it's going to be acting along where the contact is. So we can go back and redo the whole problem, and let's see if there's anything in particular. The box is still 10 kilograms. We are still pulling with 40 newtons. It's still at 30 degrees. And what they're claiming now is that we're looking at kinetic friction, 0.3. So let's take a look and see, because I wasn't sure the box would even slide. So they're just assuming the box is sliding. Let's take a look. Okay, I didn't do this as thoroughly as maybe I should have, but let's go ahead and take a look. Let's get the force diagram set up. So here is mg. Here is the normal force. Remember, the normal force is all along this surface. Here is the frictional force, also all along the surface. And then I'm pulling on this at an angle of 30 degrees, 40 newtons. M is equal to 10 kilograms. Mg is 98 newtons. The new piece of information we have now is that the kinetic coefficient of friction is going to be 0.30. And so, yeah, let's do the y direction. So in the y direction here, can we do all of this? I think we can. So in the y direction, it hasn't changed. We have n, we have components, and I haven't drawn those in either. So we've got components of force F. I got an F cosine here. I've got an F sine here. And that says in the vertical direction, I have n, I have F sine theta upwards, vertically. In the downwards, vertically direction, I have mg. So the two forces vertically upwards are matching the vertical force downwards, and I'm setting those equal. There's no acceleration taking place in the y direction. And then I'm solving for n. So n here is 78 newtons. Now remember, mg is 98 newtons, but the n value is 78, and yeah, these are the same numbers we saw back in chapter 4. So that didn't change in the vertical direction. Now I've got the horizontal direction. I've got this stuff, and then I had to fill it in down here too. So, so let's do this. I calculated the normal force. What I'm going to do is take that value of n and bring it over and say that's going to help me determine just how much kinetic friction we have. And so the acceleration that we have in the x direction, the acceleration right here, is going to be all the forces in that direction subtracting off all the forces opposing that direction. The force we have in that direction is F cosine theta. Again, draw that into the diagram. And then subtracting off the kinetic friction. And then dividing the whole thing through by the inertia. Now, the frictional force, the kinetic frictional force, oh my gosh, that does not say mu sub s, it says mu sub k. That needs to be a mu sub k for sure. Okay. All right, that's a k. Mu sub k times n, that's going to be 0.3 times 78. That gives us 23.4 newtons of friction. So what does that lead to? Well, I'm going to get, what was the force here? It was cosine of 30, it was like 30-something newtons, right? The frictional force is 23, and we have a remaining 11.2 newtons of force. So this was like 30, what does that add up to be? 34.6 maybe? 34.6 minus 23.4 is giving us 11.2, and I divide through by the inertia. It says that the acceleration we're expecting is 1.12 meters per second per second. Okay, for the acceleration. Now, a question that I have to think about here is, do I need to get this thing moving first? Once it's moving, this is describing what's happening once it's moving. But is the force we're pulling with enough to offset the static friction? Now before we were saying that the static friction was 0.4. What would that do to this number? If we're looking at the maximum static friction, what was it? Maybe we did look at this before. It was like 6, 8, 30. It's going to be around 30 newtons. So is it going to be close? Maybe it is going to be close. I think this is enough force that it slides. We'd have to go back and check. If you remember, the mu sub s that we worked with before was 0.4. I'm thinking that's going to make the frictional force somewhere around 31 newtons maybe. And if that static friction, not kinetic but static, was 31, then we would have to pull with at least 31 to get the whole process started. So there are situations where you got to pull enough initially to overcome the static friction, is what we're seeing with this. Okay, so that would be a good one to go back and run comparison numbers and see what happens. Let's see. I guess we just go back and think in terms of redoing everything that we've done with friction in place now. So this is asking, look, if I push someone on a sled, if I push someone downwards on a sled versus pull someone, the force here is lifting up somewhat on a sled, are those going to result in the same acceleration? And the idea here would be, look, if I'm pushing downwards as well as pushing forwards, that downward force is going to increase the normal force. If the normal force goes up, the frictional force will go up. So if I'm pushing down on an object while I'm sliding along the floor, that could increase the friction. Lifting upwards on the object as we pull it along the floor, that would lead to a smaller normal force, and that would lead to less friction. So it could be that what we're guessing here is that if our model works, where the frictional force depends on the normal force, this is going to be less friction than in this case, than pushing down on the person, on that object. And here we go. We do have a diagram. I wasn't sure if the diagram followed or not. So in this case, here we are pushing downward. So we got an F cosine forward. Now it's the same angle when we're lifting upward. So the F cosine here matches the F cosine there, and the F sine here matches the F sine. But the F sines are in opposite directions. This F sine theta means that the normal force then is going to be mg plus F sine theta, whereas over here, pulling at this angle, the N is going to be mg minus F sine theta. So the normal force on the right is less than the normal force on the left. If we now write down how large is F cosine, how large would F cosine need to be in terms of the frictional forces? Oh, I see. F cosine, in order to maintain constant velocity, right? So we need a velocity here that says constant. So we'll say this is velocity and it's constant, and this is velocity and this is constant. And so F cosine, in order to be, oh, it's right here. I'm sorry, I missed my own statements. So it is constant velocity. We have set the forces equal to each other. And so what we're saying is, if I want to maintain constant velocity here, I would have to push with mu sub k times mg plus an additional f sine theta, whereas in this case, I can push with mu sub k times mg minus f sine theta, so that's going to be less. So yeah, the constant velocities were there. I just have to step back away from the board sometimes to see everything going on. All right, so here's more of that same problem. So let's go back. Here's that same force diagram where we're pushing downwards with force F at some angle. Here we are lifting with force F at some angle. And what we've got, what we have here then, let's go back and look at the previous one so we can make the connection. What we said is that F cosine theta is equal to mu sub k mg plus f sine theta. So we haven't isolated f yet. We've shown that f is going to need to be bigger in this case compared with this one, but we haven't got it in final form yet. We do not have all the f's on the same side. So what we're going to do is we're going to correct that. We're going to bring over that term that had the f in it so that it's all right here, and then this is the force we would have to push with. It would be mu sub k mg over cosine theta minus mu sub k sine theta. Over here it would be mu sub k mg. Numerators look the same, but the denominator is bigger, and that means we have to push with less. So this, we're trying to get it into a form where if we were solving a problem, what information would be given? Well, they would tell us how much mass, we know what the gravitational field is if it's Earth. They would give us an angle and they would give us some coefficients of friction. Okay, so those are good diagrams to go through and stare at and think about also, what's going on at each step in that diagram. All right. Here's an interesting situation. So I've got these two boxes. Clearly, this is box 1 and this is box 2 maybe. Anyway, they've labeled them A and B. I don't know if I'm going to stick with that or not. But this is box A, it's 5 kilograms. Here is box B, it's 2 kilograms. And what we want to do is, there's a pulley, and there are going to be frictional forces maybe. Yeah, it does say that there's friction. Now, we could take the friction out and we could put the friction back in and compare to see what happens in those situations. I want to find the acceleration. Okay. Now, it's moving to the right, so they do tell us that it's not sliding this way and then making its way back. It's going to be sliding this way right from the start, is my understanding. So that's good to know. We just have to keep track of friction in one direction. So here are the free body diagrams. So for the object off to the side here, this vertical object, we've got a gravitational force, mg, and then we have a tension opposing that. So what I'm going to add to this is, to the force diagrams, I'm going to add an acceleration here, which would show up on my force diagram here. I'm going to add an acceleration here, which would show up on my force diagram there. Now, for the block that's resting on the tabletop, that's going to have a gravitational force downward. And the gravitational force is important now because that's going to help, well, it's going to determine what the normal force is, and that's going to help us determine what the frictional force is. So those are going to be related. We'll see how that all plays out. But I do have a tension in the cord, and I've got a frictional force. So that object up on the tabletop, it's got forces, 4 forces, all in positive x, positive y, negative y. Let's see what the diagrams look like. Did I change that? I did. So this is M1 and this is M2. I didn't. Anyway, the one on the tabletop I'm saying is M1. It's 5 kilograms. M2, it's 2 kilograms. And the coefficient of sliding friction, or coefficient of kinetic friction, is 0.20. That's my force diagram for block 1. Now, there's kind of advantages either way here. Notice I did not write the normal force coming right from the bottom. Maybe I should have. I did not write the frictional force right from here. This was a little quicker, but maybe I should have been more careful in placing the forces. This one looks better. So here's a tension force here, mg here. Maybe the tension's from the top. Anyway, we really just need to keep track of what direction right now these are in. So for this setup, in the vertical direction, n is equal to m1g. That's my vertical formula. Now, looking at the acceleration that's taking place, that's going to be determined by the net force. That's going to be tension minus F sub k. So it's tension minus the kinetic friction, and that gets divided by m1, which is the inertial mass. So T minus F sub k divided by m1. Now, the friction, I want to find out how large this kinetic frictional force is going to be, and we've been saying it's mu sub k times n. Now in the problem, they gave us a mu sub k. I'm going to go ahead and use it by writing my frictional force in terms of mu sub k times n. Now n is equal to m1g, so I can replace that. So the frictional force now can be directly related to the normal force, which is directly related to the gravitational force. So my frictional force can be written as a coefficient times m times g. Now, we don't always get the coefficients. Sometimes problems just ask us about the frictional force itself. They don't express it in terms of a coefficient, so there could be situations where we just work directly in terms of the frictional force. But this is an example where we're using the coefficient, and when we plug this expression in for the kinetic friction, it looks like this. It looks like T minus mu sub k m1g. Now I've solved that for T because the tension, if I solve this motion for T, I can also solve this object's motion in terms of T, and then I can splice the two equations together because the T in one is the same as the T in the other. So that's important. Remember, the tension all the way through this cable matches this one. That's going to be the case until chapter 10, where we come in and take into account the effect of the pulley. And even then, even when we're in chapter 10, sometimes we'll include the mass of the pulley, other times we'll say it's a small effect. So for right now, the pulleys are all massless. They don't create any inertia for us, and so the tensions are going to be the same on one side of the pulley as they are on the other side of the pulley. So I've taken this and I've written down the second law of motion. So the acceleration here, m2g is in the direction of acceleration, t is opposing that, and then we can divide through by m2. So I've got this solved as tension, I've got object 1's motion solved as tension. I'm going to put those two equations together. They're way down at the bottom here, but that's what I ended up with. I ended up with m1a plus mu sub k m1g equals m2g minus m sub 2a. I solved it algebraically for the acceleration. I didn't quite get all the way through, so I'm finishing it up on the next page. I solved that for a. That's what I got. Now that's interesting. The stuff on the top, the m sub 2 times g, minus mu sub 1 m1 mg, you know what that is? That's the net force driving the system of objects. Wrong direction. So here are the two objects. If I looked at external forces, what's happening with these two objects? Well, they're being pulled by gravity. Specifically, the force m2g is creating a force in this direction. Now I've got tensions in the cable, but the tensions, I have a tension holding M2 back and I have a tension pulling M1 forward. Those aren't external forces, those are internal. So what's really holding things up is this frictional force. So if I take M2G minus the frictional force, that's what showed up in my answer. So that's the net set of external forces, and the total inertia in the system is in the denominator, M1 plus M2. So that's interesting that these examples we look at, they keep showing us that this general principle of net force divided by inertia, it just keeps showing up, even with systems with more than one object. Here we have something with two objects, and that's happening. Now, I went in and I calculated all these values. So the M2G worked out to be 19.6 newtons. The mu, I guess it's just mu, it's not mu sub 1. Yeah, I guess it's kind of mu sub 1. Mu M1G is here. So the kinetic frictional force is 9.8. Now the tension is going to be somewhere between those two values. We saw this example before. First of all, let's get the acceleration solved. So putting all the numbers in for the acceleration, I'm ending up with 1.40 meters per second squared for the acceleration of that system. And then in order to solve for the tension, I can go back and use one of those other equations that I saw and that I've solved for. M2G minus M2A, using that equation, I get 16.8 newtons. So, and again, I'm just checking to see what I would expect is that the biggest force is gravity, and that tension is less than that. Tension is the intermediate one, and then friction is the lowest one. Let's go back and look at that diagram and see how that worked. So, actually we can go, let's go all the way back. So the largest force here would be M2G. That's not going to be, it's going to be bigger than the tension. The tension's not going to be as big. Tension's going to be a little less because this is accelerating. And then when I look at this, I got tension in this direction, friction opposing it. Well, if it's accelerating, the tension's bigger than the friction. So the gravitational force here is bigger than the tension, and the tension is bigger than the friction. If the static friction is large enough, the object stays in place. Now what we also had suggested here we could do, and maybe it's not such a big deal at this point, is we could ask what happens if the surface becomes frictionless? What if we decide to have the surface be frictionless instead of have friction? And in that case, we just set the mu's equal to 0. So that's a handy feature. What we can do is we can solve a problem with friction, and built into that same formula is a way to take the friction out. So if I set mu sub 1 equal to 0, then we'll have the acceleration that we had for the similar problem back in chapter 4. Now, another thing that comes out of this equation, a nice feature, is it tells us what conditions would be required to prevent an acceleration from occurring. If the kinetic friction up here, were bigger, what if the mu value here were twice as big? If the mu value was 0.6 instead of 0.3, then this would also be 19.6 newtons, and we'd have no net force. Now, no net force would tell us that the acceleration is 0, and if the object is at rest, it would stay at rest. If it's moving, it would continue moving at a constant velocity. So it could be if those two forces match, and we give it a little nudge to get it started, it should continue at constant velocity. What would happen if the frictional force were larger? If the kinetic frictional force was larger, we give it a push to get it started. What happens? It would slow down and stop. So even if we give it a push, if the frictional force now is bigger than m2g, then that's not enough of a gravitational force to keep it moving. And the object acceleration would become negative, and in the coordinate system we're using, that negative sign would tell us, the object's slowing down and stopping. Ooh, here's a problem that would be fun to think about, and it'd be fun to put on a midterm, not that it necessarily would show up on a midterm. What if we had this object like a meter away from the edge? Not sure how we would set this up. So let's say it's a meter away from the edge, and we give it a push, and then ask, is it going to slow down and stop before it gets to the edge, or is it going to slow down but not enough and then it goes over the edge? I don't know. That's the kind of thing you can start thinking about set up. And I hope these are the kind of things that start feeling more familiar, right? We can play a game like that. I can take this book and I can go, okay, I'm going to give this book an initial velocity. I'm going to give it a push, which gets it moving. It's going to start at some speed, and the edge of the table is a meter away. Is it going to go over the edge, or is it going to stay on the table, right? So, that would mean if I push it, will the center of mass end up over the table, or will the center of mass go out beyond the edge of the table, and at that point, the book tips and tumbles off the table. So we have enough in place now with our very basic model for kinetic friction that we can go in and analyze this. We can do this on an incline. We could push it along an incline, see if it goes over the edge. So for better or worse, you can start imagining quite a variety of different types of problems. All right, here we are skiing, which looks like a lot of fun. So here we are skiing, and we're trying to figure out with this ski, they're on a 30-degree slope, which I'm more of a cross-country skier myself. 30 degrees sounds pretty extreme. So here's a skier headed down a 30-degree slope at a constant speed. Now that's good, I guess. You don't want to just go faster and faster all the way down the incline. At some point you're going pretty fast. And so this skier is going down at a steady speed. They've gotten themselves at a speed that they're enjoying. So it's fast enough that they're having a lot of fun, and there's a 30-degree slope. What do we know about the kinetic coefficient of friction? So how much friction would be needed on a 30-degree slope in order to have the skier not picking up speed? The skier's not going faster. The skier just maintains the same constant speed. So let's look. We've got a normal force. Now this takes us back to the incline. We saw an example with the incline at the end of lecture for chapter 4, which was a really good example there that we were looking at. And so now we've got friction. Friction's included. So here's the normal force. Now we said back then that we're going to rotate the coordinate system. So now we've got x is along the incline, y is perpendicular. And we drew some nice diagrams there showing, and this is perfect. So here's the gravitational force. And we need to draw a rectangular box around the gravitational force because we're going to have to identify x and y components of that gravitational force. And the key thing to remember here is the rectangular box is tipped. And it's tipped at the angle of incline. So the cosine theta component is along the y-axis, and the sine theta component is along the x-axis. And every time you do this problem, stop and practice setting up those coordinates. So here it is. We've got the normal force coming from the contact point here. We got gravity, which should be coming from the gravitational point here, I guess. Anyway, so we've got gravity coming down. The gravity is being divided into a sine theta component and a cosine theta component, and we've got friction. So here is the first diagram, and there's the acceleration. And the acceleration's in this one too. They say the acceleration is 0, right? So I'm going to solve for the acceleration first because that sounds like something that would be really interesting to look at. So let's get the acceleration formula solved, and then we'll see what has to be the case if v is going to be constant. So I'm going to do this a little more lengthy, but I really want to focus in on this gravitational force here. So here's the gravitational force. Here is my rectangular box tipped so that it lines up with the new rotated x and y coordinates. And I'm going to get an mg sine theta along the incline. That's what's driving the skier downhill, is mg sine theta. If theta were 0, this would go away. But at 30 degrees, that's going to be a pretty good force. And mg cosine theta is tipped. And it's going to offset the normal. I didn't draw the other forces in here. I was focusing just on the gravity. And so coming back to over here, the acceleration in the x direction is mg sine theta minus the frictional force divided by m. Now the frictional force they're telling us is, well, it's kinetic. The skier is sliding. They didn't have to tell us that, I guess. So this is kinetic, and that we're going to say is equal to mu sub k times n. Now we got to find out what n is equal to, and so did we draw this separately? I guess we just did it all right here. So from the diagram, n is going to equal mg cosine theta, and we know that because there's no acceleration in that along that direction. The skier is not accelerating away from the slope, and the skier is not accelerating into the snow, into the slope itself. So whatever n is, or whatever mg cosine theta is, that's what n is going to be. And so we can make that substitution. We can take the n out and replace it with mg cosine theta. What's interesting here now is that the acceleration formula, there's the gravitational component, and this is friction. But they look really similar when we divide through by m. There's an m on both sides. And the m's all cancel. So the two gravitational masses in the numerator cancel the inertial mass in the denominator. And the formula simplifies down to g, just an acceleration value coming from the gravitational field, times sine theta minus mu sub k cosine theta. So if we get rid of the friction, if we set mu sub k equal to 0, it's the same formula we had in that last example in chapter 4. But now we've included friction, so the formula is more general. The formula now can accommodate frictional effects. So that's the formula that we've got in general. If mu sub k cosine theta is smaller than sine theta, the skier will be picking up speed. If the opposite is true, then the acceleration would be negative, and in this example, negative acceleration indicates the skier is slowing down. So the skier could be speeding up or slowing down depending on what the coefficient of kinetic friction is and what the angles of incline, what the angle of incline is. So those two factors. Now just to maintain a steady speed, to have the acceleration be equal to 0, I can see from the formula. This is where you stare at the formula and you go, oh yeah, I can see how to make the acceleration 0. I just have to make sine of theta equal mu sub k cosine theta. That would say mu sub k needs to be the tangent of theta. So theta then is going to be 30 degrees. And that was what was given. So for a 30-degree slope, we would need a mu sub k of 0.577. That's not small. That's a pretty good. That's a pretty good. So I don't know what's going on with the snow on this day. Going down a 30-degree slope should be enough to accelerate you if you're out skiing. Maybe you got to check the the bottoms of the skis and the conditions of the snow and see what's going on, because we've got a pretty large kinetic coefficient of friction. All right. Ooh, let's see what the next example is. We're just about at the point where we're ready to wrap things up. Yeah, the next example is going to be a little bit of detail with this, so I think this is probably a good place to stop. But I hope this is good. You know, what we're seeing now is we've been able to bring friction into these force diagrams, and I'm hoping the friction will, you know, the model that we're using for friction is simple enough that we can see some of the physics behind what's going on. The frictional forces are proportional to normal forces, and then we can come up with what feel like more realistic sorts of examples. Okay, so any kind of questions at all, stop by office hours. Looking forward to discussing any questions with you.